Now in class we saw there's three problems when we try to assign two safe arrays one to the other. If I try to say something like A is equal to B, and I have already a safe array on the left-hand side with three elements, 10, 20, 30, and I have on the right-hand side another one with four elements, 1, 2, 3, 4. Um, we saw there's a problem if you use the default assignment. There were three problems. First problem is there's a memory leak. Because what happens is the default assignment just simply copies over built-in types one to the other. So if you look at the class, basically everything in here is a built-in type. The low and high, right, those are of course integers, the upper bound and lower bound. And P, which is actually pointing into the heap, this is P over here, so that's just a pointer to an integer, and that's of course also a built-in type. So if we use the assignment that we get for free, then all that's going to happen is the 0 will get copied over to 0, the 3 will get copied over to the 2, and the pointer over here, P, is going to get copied over to here. And so what will happen is that instead of P pointing to where it's pointing here, instead of that pointer, it's going to end up pointing over to here. It's going to be breaking this link. And we saw in class that that causes essentially three problems. The first problem is as the memory leak. Right? We're not going to have that memory anymore. And so this memory on the left-hand side is lost forever. Well, in this example, it's a small amount. It's just three integers, but it could be a gigantic chunk of memory from the heap. And once we lose that, we can't recover it because the only way we know where he lives is because of this pointer, and that pointer has been overwritten. So that's the first problem. The second problem is that since A on the left-hand side and B on the right-hand side are pointing to precisely the same places in the heap, so changing A changes B and vice versa, because all the changes happen in this memory. And so that violates the basic semantics of assignment, which in C and C++ is that you just copy the value from the right-hand side to the left-hand side, but then they are separate. They're not conjoined anymore. Here, changing A changes B. That was the second problem. And the third problem is that we saw something like this. If I declare, say, let's say, some safe array, declare a safe array B outside some scope, say size 4, and then I open a scope, and I declare another safe array, say A, that goes from, let's say, 5 to 25, and I do some stuff over here, and then I say something like A gets, let's say B gets A. Then what happens is when A goes out of scope, it'll happen right here, because A has been declared in this scope. When A goes out of scope, the destructor for the class gets called, and the destructor deletes P. Well, P is the same P on both hand sides, on the right-hand side, left-hand side. So the memory, the common memory in the heap gets returned, and so when we come out of here and B tries to access its memory outside here, it doesn't exist anymore. So that's the third problem. So this is a big issue, and we can't therefore rely on the built-in assignment. So the question is, what do we do? How do we get around this? And the answer is we define our own assignment operator. Now, we're going to see that in a bit, but before we do that, there's just something that we have to understand here, and that is, what is assignment actually going to do? So, generally, we're going to define our own operator assign. Right? We overload assignment. Operator equal. And what's going to happen is, if I say something like A is equal to B, it's going to be A dot operator equal, and B is going to be the parameter. Right? That's what it really means. We're going to write it A is equal to B, but C++ will say A dot operator equals of B. That's what's going to happen here. So that means A is going to be the left-hand side, and B is going to be the right-hand side. So now, whenever we want to talk about the upper and lower bounds, for example, of A, or the P of A, so we're simply going to say low when we talk about the lower bound of A, and we're going to say high when we talk about the upper bound, and we're going to say P when we speak about the pointer to the heap. But how do we end up talking about the lower and upper bound in P of B? So we're going to have some parameter. We're going to have, say, some parameter S. We're going to say we're going to define operator equals, and we're going to say, and there's going to be some parameter which is going to be some safe array. We'll see in a moment, and that safe array is going to be called, let's say, S. And so it's all going to be in terms of S. So if we want to talk about S's in other words, the parameter is low, we're going to have to say something like s dot low in our assignment. If we want to talk about the high, we say s dot high. And if we want to talk about the pointer p, we have to say s dot p. Now, how does that happen? How does the compiler arrange so that if I'm talking about the thing on the left-hand side, I'm talking about A's member variables, data members, just use the letters themselves, and on the right-hand side, if I want to get the parameters, I have to use the parameter name. How does it know where A and B and C are located in memory? Okay, because if I have 20 different safe arrays and I say low, high, and P, I mean, how does it know which one I'm working on, right? That's an important question. How do I know which one I'm working on? So the answer is, and this we haven't seen before, the answer is that C++, when you have a member function and you pass parameters into the member function, it always passes an additional parameter, one more than you expect. So for example, if in our case over here, this operator equals, so even though it looks to us, right over here, it looks to us that operator equals really has only one parameter, right, namely b in this case, when we say a is equal to b. In fact, it also passes an additional parameter, and that parameter is going to be the address of the object on the left-hand side. It's going to take its address and pass it in. So we don't write it like this. We can't write it like this. We're going to write a is equal to b, and we can also write it as a dot operator equals of b, but this gets transformed by the compiler into the following. This right-hand thing over here, this actual call in the function, gets translated into a dot operator equals, and it's passing in two things. It's passing in, number one, a pointer, and it calls this pointer this. And the second thing it passes in is it passes in b itself. Now, instead of this, I mean, it's going to call it this in the function. What it's really passing in is the address of the A. So that's an additional parameter. We don't even see that thing. That gets passed in automatically. And every time we have a member function, if we think there really are n variables, there's really n plus 1 variables, the first one being passed in is the address on the left-hand side. In the function itself, when we actually write operator equal, we can access this parameter. This parameter gets placed in a special variable, as we said. The name of that variable is this, and the type of this is a pointer to the class type. So in this case, since we're dealing with safe arrays, the type of this is going to be a pointer to a safe array. Now this is going to be important because we're going to need this when we actually see how to write the assignment operator. Okay, so that's very important to understand. Again, just to make sure this is clear, when we have member functions, so the member function always has an additional parameter passed in. It's the address of the object upon which the member function is being called, not the parameter, but the object which is called, the one on the left. And in this case, it's going to be A, right? That's the one on the left. It takes the address, it passes the address into whatever the member function is, in this case, operator equal, and we can use that address if we need to know the address of the object on the left. And the compiler does use that in its own work, because when it lets us say something like, to access directly the variables on the left, we say, for example, as we saw, we'll be able to say something like low if we want to access A's low, and high if we want to access B's low. The reason that works is that when we say something like low, right, and I mean low on the left-hand side. So if I just say low, meaning the low of A, the compiler internally has translated that into, well, I know where the guy on the left-hand side lives. He is this. So how do I get the low of the left-hand side? How do I get that data member? Well, I could just dereference that. So I take this and I say this arrow low. Right? So even though I write low, and I mean low on the left-hand side, low, the compiler is writing this. Just in case you don't know what this arrow means, basically what it's doing is it's taking this. This is equivalent to, it's taking this, which is an address, which is the address of the left-hand side, and it is dereferencing this, so giving me the name of the object on the left-hand side, or a reference to it, and then it's taking dot low. So these are synonymous. This arrow low means the same thing as this. Okay, now this is going to be important because then we can understand how assignment in fact works. Take a look at that in one moment.